别的还没看呢，不让我讲。身份证他并不拿去的。你没当时。把三个弄完之后就不会跟你也长，所以比如说要检查它
笔是吗？啊，你可以。
上，反正我他妈没在吵，没在吵。
我直接在火爆别吵。
我就还挺出来的，我这是勒子，我上是勒子。我在我已经下面，他应该在对，他有点干。我单位长发。不是上星期给了不是这个，是给问实验室才好玩的，别太小，内心总是那
听不出来。
英语，Oh no, it's from the library. 30Yeah, maybe too high. Yeah. They want to do it on site. Instead of
Okay, so welcome to today's seminar. Before we start, I just want to make an announcement. We run a competition every year among graduate students through presentation. And in the past, we used to have to ask the students to give a full seminar, about 15, 20 minutes. And we run this as a competition, and we have a judge, and we have the prizes for the winners and certificates. This year, or in the past also a couple of years, we have been running it through the 3MT, which is a 3 minutes presentations. So I believe that our presentations, this competition will be on November 15th. So I would like to encourage you to try to sign up for these presentations for the 3MT. It's excellent experience for you. And it's good for your presentation skills. We listen to your presentation and we provide you some feedback. And also you have a chance to win. It will be very good on your CV, on your resume. And there is a small, as I said, cash award associated with that. So please try to benefit from this opportunity. In addition to that, it's milestone in your graduate program. So if you are doing MSc or PhD, you need to do one presentation throughout your study time. So please try to make sure that you do presentation during the time you are here. Okay. That's regarding that. And I would like to introduce the speaker. Usually I would like to come and introduce our new faculty members because this is our biggest strength. We are very proud of people we hire here. We are very selective in our hiring. So usually we hire excellent researchers and excellent teachers as well. So I'm coming today to present Dr. Wang. Jen, she joined the Department of Civil Environmental Engineering in July of this year. Her area of research is wind engineering. So she is complementing our existing strengths in this area. So she's between wind and structure, like myself. And she is very knowledgeable about what she does. She has two dual PhDs from Tongji University in China, together with Clemson University in the United States. And I know that she does very thorough work on the effect of strong wind storms, including tornadoes, on low-rise buildings, which is very important subject. Okay. So unless Dr. Beng Li has any announcement to make, do you want to add anything? Okay, so if that's the case, then I would invite Jane to start her presentation.
Okay, thank you, everyone. Thank you for coming for this seminar, my presentation. Today, I want to talk about the determination of wind loads on main wind force resisting system of rigid buildings. I think this is very important for all of us, civil engineers, structural engineers. Okay, I think the most important method or framework to determine wind loads is Davenport wind loading chain. Davenport, we all know Davenport, right? Especially at Western here, the boundary layer. He's the father of wind engineering. This is a very beautiful wind loading chain, including 5 components. The first one is wind climate, like the wind speed and the profile, the turbulence intensity. And the second term is influence of terrain. The smooth terrain, open, suburban, something like that. And third component is aerodynamic effects, which is the interaction between the structure, the building, and the wind field. And the fourth term is dynamic effects, including the wind turbulence effects on the dynamic wind loads and also the structure readiness. And the final term or the fifth term is actually the criteria, the code, the load provisions, such as ASCE 7/2022. So the equation to represent like these five, the first four components are given here. And the first and the second components are marked in red here. V here is the wind velocity, and all the parameters indicates the influence terrain. And the third one is the aerodynamic effects, CP. This is the pressure efficient coefficient. And the parameter to represent the dynamic effect is termed as G, Gust effect factor. That means that the combination of CP and G together determine the dynamic wind loads or the peak wind loads on structures, on buildings. And this framework is actually based on quasi-static theory, which I will discuss in detail in the following sections. And in the presentation here, I will talk about the pressure coefficient and the Gust effect factor. This is very important for the determination of wind loads on structures. The aerodynamics or the interactions between the structure and the wind field is quite complex. Let's look at this figure here. This is a typical square cylinder. And when the wind is coming this way, the flow will separate in front of the building and generate horseshoe vortex. This horseshoe vortex will go around the building and influence the pressures or the loads around the building. This is a very typical fluid mechanics associated with structure here. And due to this complication of the aerodynamics or the interactions, the building shape will influence the aerodynamics of the structures. In the wind engineering, the greatest challenge is to the determination of the fluid mechanism around the buildings with different shapes. For example, for this very flat building, such as the low-rise building, the flow will mainly go top the building. While for the very slender buildings, such as the high-rise buildings, the flow will mainly go around the building. So these different fluid mechanics indicate that the different parameters of the buildings will influence the fluid mechanism. For the low-rise building or very flat building, the roof height is important. While for very slender or high-rise building, the breadth B, which is the plane dimension across the wind, is important. And the question arises, do aerodynamics depend on the non-dimensional geometric parameters, such as the height ratio, H/L, plane aspect ratio, L/B, or another ratio, H/B? Note that the L and B is the parameter of the plane based on the wind direction. L is a plane dimension along wind direction, and B is a plane dimension across wind direction. This is quite different with like the seismic engineering or something like that. The wind engineering is quite influenced by the building shape here. And in our commonly used load provisions, such as ASCE 7/22, there's a chapter 27, which gives the pressure coefficient based on the non-dimensional geometric parameter. For example, for the low-rise building uplift, this chapter gives the pressure coefficient as a function of H/L. And for the wall pressures here, like the windward wall, which is the front wall, and the side wall, chapter 27 only gives a single number, single value, a constant value here. But for the leeward wall, which is the back wall of the building, the pressure coefficient is depending on the plane aspect ratio, L/B. but we want to ask, can ASCE 722 or the code provisions accurately estimate the wind loads of rigid buildings for any building configurations? As I mentioned in the first slide for the Davenport wind loading chain, the wind loads in many code provisions are developed based on quasi-steady theory. So here I will give the discussion for quasi-steady theory. Quasi-steady theory is actually a concept that assumes that pressure fluctuation is a function of the upstream turbulence, which is expressed in equation here. The P is a wind pressure, P bar is a mean wind pressure, P prime is a fluctuating wind pressure, and V bar and V prime indicate the velocity, mean wind velocity, and fluctuating wind velocity respectively. So based on quasi-steady theory, the fluctuation of wind pressure is linearly related to the fluctuation of wind speed. We can use this figure to clearly show the linear relationship between the wind loads and velocity. Due to this linear relationship between wind loads and velocity from the spectrum domain, we would assume that the wind load spectrum is linearly related to the velocity spectrum. However, we want to ask, does this happen in real world? No. Due to the flow distortion around the building, around the structure, the relationship between the velocity spectrum and wind load spectrum is nonlinear. And we give a function named aerodynamic admittance function to represent the nonlinear relationship between the wind load spectrum and velocity spectrum. Therefore, the spectrum of wind loads is nonlinearly related to the velocity spectrum using this equation. Okay, and now we develop the Gust effect factor model to account for the upstream wind turbulence on the dynamic wind loads. This Gust effect factor has two assumptions. The first one is wind loads follow Gaussian distribution. This is because in wind field, we usually assume the wind flow is Gaussian distribution. And the second assumption is border generated turbulence is not taken into consideration. Only the upstream wind turbulence is accounted for in the Gust effect factor model. Davenport has developed, was the first one developed the Gust loading factor to consider the upstream turbulence effect on the dynamic wind loads. And later, Professor Solari gave a very beautiful equation named for Gust effect factor model here. And this model has been widely used in many code provisions such as ASCE, Canadian code, NBCC, and European code. In this equation, there are two parameters actually influence the accuracy of Gust effect factors. The first one is the GP peak factor. This is actually reflect whether or not the wind loads follow Gaussian distribution. And the second parameter is the aerodynamic admittance function here, which actually related to the second assumption, whether or not border generated turbulence affect the wind loads, dynamic wind loads. So in order to accurately evaluate the wind loads on structures, on buildings, we need to know the aerodynamics of the buildings, like the mean pressure coefficient very well. In addition, we need to know the Gust effect factor very well. So it means that we need to know well the peak factor and aerodynamic admittance function. And here in this table, I gave the Gust effect factor model in ASCE code. The left first column indicates the Gust effect factor model in ASCE for any buildings. And the middle column here is a simplification of Gust effect factor for rigid buildings, which means ASCE 7 only provides a constant Gust effect factor for rigid buildings. The rigid building here means that there is no structural resonance due to the wind fluctuation. And here in my analysis, I use the original format of Gust effect factor. And in order to evaluate the application of Gust effect factors for any cases, I use this method and compared with the ASCE model and the constant number. So the second objective in this presentation is to evaluate the application of Gust effect factor model for any building configuration. Okay, I will give the summary of the objectives in this presentation. I want to complete two objectives. The first one is investigate the effects of non-dimensional geometric parameters on aerodynamic loads, and examine the wind load provisions in ASCE 722. And the second objective is to study the body-generated turbulence effects on aerodynamic admittance function and statistical distribution of wind loads, which means to examine the body-generated turbulence effects on Gust effect factor. Okay, let's look at the aerodynamics. Before I show the results in this analysis, I will give the terminology used in my analysis. The building shape influences the aerodynamics, influence interaction between the structure and the wind field. Therefore, all the dimensions along with this building is depending on wind direction. For example, the L is the plane dimension along wind direction. B is plane dimension across wind direction. But D and W indicate the largest and smallest plane dimension of the building here. So for the case one, which means wind is coming this direction, B is the plane dimension across wind direction. So B is W and L is D. For another direction, case two, B is D and L is W. This is quite different. You should be very clear with this terminology used here, because all the results I will show below is based on the terminology I used in this slide. In order to systematically study the aerodynamics for any building configurations, we need a very large data set, including as much as building configurations. So the first data set I used is NIST data set. This data set including 36 building configurations, but in my analysis, I used 28 building configurations for low sloped roof, which means all the roof slope angle is smaller than 10 degrees. And this data set has so many building models with different plane dimension and roof height. But all these data sets are for the low-rise buildings. So in order to get more data for other building configurations, I created another data set for higher buildings, mid-rise buildings, and high-rise buildings. This data set includes 30 building configurations, and I classified the 30 buildings into 5 groups based on different height ratio, H over W. W is the lowest plane dimension of the building. So the height ratios are ranging from 1 to 12. And in the presentation, I will use different markers to indicate 5 groups. For the lowest group, the black box indicates the lowest group, while for the highest building, I use the green star to indicate this group. Okay, then the results come. Before I show you the results for the roof or the sidewall pressures, I want to give a description on the fluid mechanism around the structure around the building. This is a very typical 2D, two-dimensional structure. When the wind is coming this way, it will separate at the leading edge of the structure and form a separation bubble above the building surface. And when the building is long enough, the separated flow will reattach on the downstream of the surface here. And this fluid mechanism, the separated flow, significantly influence the pressure distribution on roof and sidewalls. So here I will show you the results for roof and sidewalls. This is a contour plot for the pressure distribution over sidewall and roof. As I mentioned in the second or third slide, the flow will mainly go over the building for very low or very flat building, low-rise building. Therefore, roof height is very important parameter. So in this contour plot, I use roof height as a normalization parameter. We can see that the pressure pattern over sidewall and roof are very similar. The white line here indicates the different zooms on the sidewall or on the roof. Close to the leading edge of the roof or sidewall, there's a very strong suction here. And far away from the leading edge of the roof or sidewall, the pressure magnitude is reduced here. So the objective, as I mentioned, the objective in this presentation is to examine the non-dimensional geometric parameter effects on the pressure distribution. This figure here shows the uplift, the trend of uplift with non-dimensional parameter H/L for low-rise buildings. Here I separate the results for low-rise building and mid and high-rise building because the fluid mechanism for the different buildings are quite different. Let's look at the low-rise building first. All the black and blue markers indicate the wind tunnel test for NIST database for low-rise buildings. And red markers denote the load provisions from ASCE 7. There's a very beautiful and clear trend with H/L for low-rise buildings. And the code provisions can capture this trend very well. And also the code provisions overestimate the low-rise building uplift. However, for the mid and high-rise buildings, the non-dimensional parameter affecting the uplift is L/B, not H/L. And also you can say the overall uplift over higher buildings, mid-rise and high-rise buildings increase with roof height. And this trend cannot be captured by ASCE code. This is also why I want to do the analysis. And these results will contribute to the codification of wind loads in ASCE 7. Similarly, I did the same thing for area averaged sidewall pressures. As I mentioned, the fluid mechanism for sidewalls and roofs are very close, similar. They're all driven by the separated flow over building surfaces. Therefore, I did the same thing for sidewall pressures. And the distribution or the trend of sidewall pressures behaves the same with the overall uplift. However, the load provisions in ASCE 7 only gave a constant number for sidewalls, -0.7 here. Even though this number is conservative for many cases, however, it's not accurate enough. So from the viewpoint of economics, it's not economical. And we want to know how close between sidewalls and roofs which will be given in this figure. The x-axis is the roof, and the y-axis is sidewall. The blue line with slope of 1/wall indicates the perfect fit between sidewall and roof. All the wind tunnel data follow around this line, indicates the sidewall is quite close with roof. What this figure can give us is that probably we can use roof or sidewall. We can use roof to design sidewall or use sidewall to design roof. Then let's look at the leeward wall pressures or the back wall pressures. Here I give the contour plots of the pressure distribution for low-rise buildings. The below figure indicates the pressure distribution over roof, and the upper contour plot indicates the pressure distribution over leeward wall or back wall. You can clearly see that the leeward wall pressures are very close to the trailing edge of the roof because all the leeward wall or back wall are influenced by the wake of the building. And this wake is actually influenced by the separated flow over building surfaces. And this gives us a hint that the leeward wall might be influenced by the same non-dimensional geometric parameter as uplift over roof. And this is examined in the figures here. The left figure is for low-rise building, and right figure is for mid-rise and high-rise buildings. All the trend of leeward wall pressures is similar with overall uplift or sidewall. For example, the leeward wall over low-rise buildings is linearly increased with H over L. And for mid-rise and high-rise buildings, all the three dimensional parameter H, L, and B together determine the distribution of leeward wall pressure. And also leeward wall pressure increase with roof height. However, we can conclude that the load provisions in ASCE 7 cannot accurately capture this trend of real or actual wind pressures. So the previous slides mainly focus on the suction or the negative pressure over building surfaces, the roof, sidewall, and leeward wall. Here I will show you the results for the positive pressure on windward wall or front wall here. I gave the pressure contour plots for 4 different buildings with different height ratio H over B. B is the plane dimension or cross wind direction here. You can see that for higher building with higher height ratio H over B, there is a very strong positive pressure on the windward wall. While for low building here, the positive pressure is reduced. So from the contour plots, we can know that the non-dimensional parameter is off. The non-dimensional parameter H over B influence the windward wall pressures, which is examined in the figure in this slide. That figure makes all the buildings from low rise to high rise, and the red dot indicates the ASCE code. And right figure is just for low rise. Okay, so let's look at the all the buildings first in the left figure. ASCE code provisions is conservative, but it's wrong. Unfortunately, it's wrong, especially for the low-rise buildings. The low-rise buildings has a clear trend with H over B and keep almost constant for the middle range, H over B greater than 0.4 and smaller than 1. However, ASCE code has a reverse trend with H over B for lower buildings. And for high-rise buildings, very slender buildings, the windward wall pressures almost keep constant and very close to the ASCE code provisions here. this figure gives the explain why the windward wall pressures is depending on H over V because of the horseshoe vortices in front of the building here. And this horseshoe vortices is mainly influenced by the separation point in front of the building here. And this separation point is actually influenced by the aspect ratio of this building, H over V. So from the fluid mechanism here, we know that the non-dimensional geometric parameter influence the pressure distribution over building surfaces. Okay, another key reaction I want to show you is the base shear or the thrust for the low-rise and mid and high-rise buildings. So for the left figure, we can see that the base shear for low-rise buildings increase with H over V. And this trend is very close to that of windward wall pressures. For the mid and high-rise buildings, the base shear is a function of L over V. And this is close to the trend for leeward wall. It's because for the low-rise buildings, windward wall is important, while for high-rise buildings, leeward wall is important. So due to the different mechanism driving base shear, the key parameters influencing base shear is quite different here. And from the previous slides, I showed that the complex fluid mechanism over buildings, like the separated flow for roof, sidewall, and leeward wall, and horseshoe vortices for the windward wall. And all the fluid mechanisms are influenced by different non-dimensional geometric parameter, like H over L, H over V, and L over V. And based on the fluid mechanism, we classify the mid-rise and high-rise buildings. And this is also novelty in my research because this is to my knowledge, this is the first time we gave a clear definition of mid-rise building and high-rise buildings. Before that, for buildings with height ratio smaller than 1, all the fluid mechanisms are influenced by the roof height. So these buildings are defined as low-rise buildings. And for the buildings with height ratio greater than 4, the plan dimension aspect ratio L over B is a key parameter. And these buildings are defined as high-rise. While the middle buildings with height ratio between 1 and 4 are defined as mid-rise buildings. And the key parameters for these buildings are actually at the trending stage. All the three parameters H, L, and B together influence the fluid mechanism for the middle. And here I want to give conclusions for the aerodynamic dynamics or the interactions between the structures and the wind field. Firstly, for the uplift or the sidewall pressure and leeward wall pressures, we can conclude that H over L work well for low-rise buildings. While for the higher buildings, mid-rise and high-rise building, all three parameters together determine the pressure distribution. And our code provisions in ASCE 7 can accurately capture the uplift trend for low-rise building, but this does not for mid-rise and high-rise buildings. And for the positive pressures on windward walls, we find that the non-dimensional parameter H over V works for this tested building. And when the windward wall is very tall with very great aspect ratio of H over V, the windward pressures keeps almost constant. And ASCE 7 code cannot accurately. So here from this conclusions here, I want to give you a very deep understanding on what is aerodynamics, what influence aerodynamics. And if what is the strengths or shortcomings of ASCE code and how to improve this code. And for structural engineering, how to design such as high-rise buildings more accurately. And the second aspect I want to talk about is a Gust effect factor. This is very important. It actually gives a relationship between the turbulence with the fluctuation of wind loads here. Okay, this figure comes again. For this fluid mechanism for this typical building, we already know that the horseshoe vortices in front of the building greatly influence the windward wall pressures on the front wall here. So one may ask, how does this horseshoe vortex influence the Gust effect factors? Because for the development of Gust effect factors, the body generated turbulence such as horseshoe vortices are neglected. So in order to evaluate the Gust effect factors, we need to examine the assumptions in Gust effect factors. There are two assumptions in Gust effect factor, and the first one is the Gaussian tail of wind loads. So firstly, I will examine if the wind loads follow Gaussian distribution by examining the skewness and vortices of wind loads. For skewness with 0 and vortices of 3, the wind loads follow Gaussian distribution strictly. And from the figures here, we can see that the wind loads on windward walls is depending on H over B. For very high buildings with H over B greater than 4, the skewness and vortices are tending to 0 and 3 respectively, indicating this building follow Gaussian distribution more closely. However, for very low buildings, low-rise buildings here, both the skewness and vortices exceed the 0 and 3. So these buildings follow non-Gaussian distribution. And this finding conflict with the assumption in Gust effect factor, indicating the application of Gust effect factor deserves further investigation. And the second assumption in Gust effect factor is the ignorance of body-generated turbulence. So I want to examine how body-generated turbulence influence Gust effect factor here from spectral domain. The left figure is the spectrum or the energy content of wind pressures, while the right figure here is the aerodynamic admittance function. This relates the fluctuation of wind loads to wind turbulence. We can see that for the aerodynamics at the non-dimensional scale f, square root v multiplied by h divided by the loop height, wind velocity at medium loop height smaller than 0.1 here. The aerodynamic function is depending on height ratio H over B. And this actually influenced by horseshoe vortex on the body generated turbulence. So we can conclude that the body generated turbulence is very important for the aerodynamic admittance function of for the spectrum of the wind loads. And the assumption in Gust effect factor by ignoring the body generated turbulence is wrong. And then I will show you the Gust effect factors, the measured Gust effect factors, and the models, Gust effect factor models. The black dot and the red dot indicates the model, Gust effect factor model, with and without the 3-second gust, while other markers indicate the measured Gust effect factor for wind tunnel. For very high buildings in this figure, it will be greater than 4. measured Gust effect factor is approaching to the storage model. Well, for lower buildings, the Gust effect factor model will underestimate the measured Gust effect factor. And this is another finding actually in my analysis. It's very interesting that we conclude for lower buildings, the horseshoe vortex is very important. While this effect is minimum for high-rise buildings with height ratio H over B greater than 4. And the middle buildings are actually at the transit stage. And this is the aerodynamic admittance function for sidewalls and roof for very high building, H over W greater than 12. You can see that for sidewalls, there's a peak around this frequency, reduced frequency, 0.1. This is actually influenced by the vortex shedding. While for uplift here, the measured aerodynamic function divide with the model. Sorry, model or Bakery model because of the separation bubble. And this gives the results for the Gust effect factors of sidewalls and roofs and compared with the model. The conclusion is the same actually, the same with the windward walls. We can conclude that the model, by ignoring the body generated turbulence, will underestimate the real Gust effect factors. And the conclusions for that effect factors is here. The same, I want you to know that how to evaluate the peak wind loads by using Gust effect factors through this presentation. Okay, the previous slides is the analysis of the study in my past, in my postdoc, and this is I want to talk some about the tornado, which is the topic in my current stage. Tornado, what is tornado? Tornado is a small-scale, three-dimensional wind event. It's quite different with the boundary layer wind. So the building model size relative to the tornado size is very important. In addition, the tornado wind field is quite complex. There are many different.
We want to give some time for questions. So I
okay.
suggest we can have another lecture for tornadoes.
Okay, yeah, it's very simple. This is the last slide. Okay, so I want to say that for tornadoes, there are many different aspects in tornadoes compared with boundary layer winds, such as the velocity profile and the pressure drop associated with tornado. So we want to know how to determine tornado-induced wind loads. Can we use the framework developed by Davenport wind loading tree to evaluate tornado wind loads? This is unknown. There's a research gap in this area, and this is what I want to do in my near research study. And I want to use the windy dome here in Weston to investigate the tornado effects on structures. Yeah, and this is my current topic in my early career as assistant professor, and welcome any students who are interested in this topic. Okay, thank you.
Two things related to what Jen has presented. One of the papers she has presented its results won the best paper award in the ASCE, Journal of Structural Engineering. And the second thing that her work now is in the process of being implemented in the ASCE 7 code. So those are very good things, and that shows the impact of the research. That's very important, the impact of the research. In addition to publishing paper, we always look to the impact of the work. So maybe you have time for one quick questions before 2:20, because I see there's a group of students waiting outside. If any person somebody has a quick question. Okay. Yeah, maybe.
I'm not sure on which slide, maybe on slide 30, you were trying to show us how the horseshoe vortex is like playing a part, and you are showing it with the spectra and also the aerodynamic admittance function, but I didn't understand exactly how it correlated to them.
Okay, yeah, because the aerodynamic admittance function is actually a function reflecting the relationship between the wind loads and wind turbulence. So if the quasi-steady theory works best, which means the aerodynamic admittance function is unit, is 1. So if the aerodynamic admittance function is not 1, this means there the body generated turbulence influence the fluctuation of wind loads. And from my analysis, all the aerodynamic admittance are behind 1, above 1, or lower than 1. This is caused by the body generated turbulence.
I think we have contacted some of you as TAs to attend the meeting today at 4:30. So some of you might have received an email from Naira. So if you receive this email, please try to attend this meeting today at 4:30 p.m. The email will be from Naira for people, some of the TAs. Okay.
Let's give one last round of applause for our speaker.